That's my border. I was just dancing. Oh, I didn't draw that straight at all. Bad. It's totally recording right now. Oh, you have nice pictures of atoms.
I can't remember anything. Like brain dead.
You're brain dead, you can
What?
physically dead.
Yeah, well,
If you're pronounced brain
I
dead.
know, but I was being sarcastic.
I know.
Yeah.
Just kidding.
Now you're just confusing me.
Alrighty. So as I walk around, I'm noticing a couple things. Some of you have a better sense of what an atom is like than others. And I am going to hopefully reinforce your idea of what the atom looks like, even though I can't see it, but our idea of what the atom is like with a story. And hopefully this meaningful story will allow you to never forget, because I know for a fact that you've been learning the structure of the atom from when you were a little scrapper, a wee one, an itty bitty. Okay? So I'm going to tell you a story, and it is the story of a place called Matterville. I am going to ask that you stop writing on the boards in the meantime, because you're using my ink. And I would like you to write down what I write on the board, because we're going to talk about what atoms are like with this story. And it will hopefully create an image in your mind that never goes away. All right. And so I would like you to put this in your notes, wherever your notes are. Anything that we covered today or tomorrow is fair game for the quiz on Friday. So we're going to be doing lab safety stuff, but also what we covered today and tomorrow. So here's this place. It is called Matterville. Okay, in the center of Matterville is a special place called the Nucleus Arcade. You guys know what an arcade is? You know, back in my day, it was the place where you went to play all the video games, and that was the only way you got to play video games, essentially, unless you had an Atari. All right, this is the Nucleus Arcade. I am also going to ask that you not be mumbling under your breath or talking, because I am recording right now, and it is broadcasting live on YouTube. So, blank stares. So, Nucleus Arcade. Now, in the Nucleus Arcade live a couple ladies, and for the sake of not sounding mean, I'm just going to say that they're big boned. They're husky ladies. And they could very easily be husky men, but in my story, they're ladies. All right. So the first lady, her name is Positive Patty Proton. She has eyes that sparkle. Again, she's a larger gal. And she is wearing clothes, and she does have hair. I'm going to draw the hair, but I'm not very good at drawing clothes. So you can draw your own clothes as you see fit, but please rest assured that this is not the type of arcade where they are there without clothing. It's not that kind of arcade. They definitely are wearing clothes, even though my drawing does not show clothing. So positive Patty Proton has eyes that sparkle, this sunshiny personality, happy-go-lucky, always positive. She can turn any situation into a positive one. So she's just chilling there in the Nucleus Arcade, and all of a sudden her grandma calls up and says, Patty, I have some tragic news. I'm afraid your dog Buster was hit by a car. And rather than become sorrowful, instead of being filled with sorrow, she tries to look at things in the most positive way and says, you know, he was up there in age, and at least he didn't suffer. You know, so she really tends to look at things in a very positive way. Also in the Nucleus Arcade is Nerdy Nell the Neutron, who has kind of a blank stare. She's also a large gal. She's got curly hair. Now, she has a personality that is very neutral. She doesn't get excited about anything. She doesn't become happy. She doesn't become sad. She's just there. This is really hard to do. Nerdy Nell the Neutron, she's got a tough job. She's got to keep her. I'm trying to keep my face neutral. How am I doing? I can't do it. So Ed McMahon comes to the Nucleus Arcade and says, Nelda, you have won $1 million. How does she react? This is it. She's not smiling. All right. So kind of a blank stare, doesn't get excited, doesn't get happy, doesn't get sad. She has more of a neutral disposition. All right, so the ladies in the Nucleus Arcade, they're both about the same size, which is husky. They shop in the that part of the store where I usually find good deals. They're not tiny. All right, around the Nucleus Arcade are some roadways. We have Electron Street, the Electron Highway, and the Electron Super Freeway, Autobahn, Interstate. All right. On these roadways exists a character whose name is Enraged Elliot Electron. He's riding very quickly on his chrome-plated Harley Davidson. I'm going to try my best right now at drawing a Harley Davidson. I haven't had a lot of success. So this is the gas tank. And it's going to be kind of decked out. These are some flames. There's kind of a spot there where the handlebars are attached. They're the big ones, you know. They sit out like that. I guess there must be a seat there. And maybe a little spot where Enraged Elliot Electron can... No, he doesn't have anyone ride with him. And then I guess there's got to be a spot here to put the feet and some other stuff right in here. I don't know what it is. I don't know what a Harley Davidson is made up of. All right, and then we got something filling there, and then we have a big long tire. Or what's that thing that connects the tire? Is I don't know what connects the tire to the rest of the bike. What's this called?
Spoke.
No.
Before.
Yeah,
All right, this is my Harley Davidson, and that's Elliot. What do you notice about Elliot that is very different than the other ladies? He's very skinny. In fact, his head's probably only, like his whole body's probably that big comparatively, but I decided I'll just blow up his head a little bit. He is angry much of the time where his eyes are like, closed, shut, and he is scowling much of the time in anger because the ladies won't let him in the Nucleus Arcade. Very negative disposition. Now, he can exist on any of these roads at any time, but he can't go through the ditches. He can't do that. But he can be on this road, and he can manage to get onto this road. If he can manage to get there, he can ride there. How could he possibly get from one road to the other without going through any ditches?
Jump.
He has some sweet jumps. All right, so here's my sweet jump. It's not the best, but if you can imagine, he can jump from one to the next. Now, each of these roads are of a certain size, and there's only enough room for a certain number of Elliot and his Electron brothers. Does anyone have a speculation for how many Electron brothers, Elliot brothers, would be able to ride their Harley Davidsons on this first road? Dan? And what are you basing this on? All right, so you're thinking of electron shells. You learned it in probably high school science, also in maybe in biology a little bit. How many in the second? 8. I hear an 8. So I'm going to write 2. That is absolutely right. There's only enough room for 2 Elliot brothers. And the second can hold 8 Elliot brothers. How about the third? I hear an 18 and I hear an 8.
18 counting all of those.
All right, so you're kind of thinking 288 weird.
Yeah.
Yeah, they lied to you. It's a sham. But they just told you a little fib to make things as easy as possible. It can actually hold up to 18 Elliot Electron brothers. Now, there's something special about 8. And we're going to learn something called the octet rule, because there is something special about 8. And if this outer electron energy level has 8 Elliot electrons, it's considered a stable arrangement. It doesn't matter how many it could fit. If there's 8, it's great. The fourth road can hold up to 32 Elliot electrons. But if there are 8, it's great. If there are 8, it's great. So there is something about the 8. But it is 2 in the first energy level on this roadway, 2 Elliot electrons in this one, up to 18. But in your experience with the first 18 elements that we've learned, you haven't ever put any more electrons than that in there. Okay? So let's say that if we look at Matterville, we have one positive Patty, we have one nerdy Nelda neutron, positive Patty proton, enraged Elliot electron. We have one of each of these people. How would the overall morale of Matterville be? Positive, negative, or neutral? All right. We have one Elliot electron, one positive Patty proton. They would kind of balance each other out, right? What if Elliot leaves? Because he can leave. Which would leave behind an overall positive. Yeah, get rid of that crabby pants. He leaves. Ooh, much happier place. So what if Elliot from a neighboring town gets some electron brothers and they come to Matterville? How does the overall morale of Matterville change? It becomes more negative. So if electrons are added, you got a lot of crabby pants in there. That overall crabby negative attitude. If electrons leave, leaving behind a more positive, happy place. Just for the record, atoms don't have feelings, and this isn't a real place, but it's an analogy, it's a story. Okay? Now, I want you to draw a picture of an atom and label its parts on your whiteboard.
Like a motorcycle.
Yeah, yours is much better than mine. So some of your drawings are not going to change much because you had a good sense from the beginning, but I see that some of your drawings are changing quite a bit. What happens if I add more nerdy Neldas to the Nucleus Arcade? How's the overall morale change? So I'll ask again because I think that you guys are in some weird place. If I add some more nerdy Neldas, what changes in Matterville? The morale doesn't change. What about the mass?
Yeah.
It gets heavier, right? So all of the mass is in the nucleus, and if we have more nerdy Neldas, it's going to make that nucleus heavier, which can happen. If you add enough nerdy Neldas, it can make the nucleus unstable, and you could get a nuclear sort of reaction. I have a resource for you. I feel like I forgot something serious with this story.
Valence.
No, I didn't talk about that just yet. And I didn't mean to either.
Got it.
It's my money in here.
Let's open the window.
Can't open the window.
Oh, the rain's coming.
Okay, I'm giving this to you as a resource. You can see it has the basic structure of an atom there. It shows that in the first, they're called energy shells or electron levels. In the first, 2 electrons can be held. In the second, you can have up to 8. And in the third, up to 18. But if there's 8, it is great. It's considered stable. And there's a lot of opportunity to talk about that shortly. What I would like to do in your notes is I would like us to summarize this table right here. And I'll write it on the board as well. So if we summarize, so this is, we're going to call it a particle. We have the proton, the neutron, and the electron. We're going to look at its symbol. We're going to look at its mass. We're going to look at its charge. In addition to that, we're going to write location. Okay, so the symbol that gets used for a proton is a P with a plus. The symbol that gets used for a neutron is an N with a little 0. And it's kind of written like as a superscript, like as if it were being squared, so kind of up and to the right. The symbol for an electron is E with a negative sign. They're all lowercase, and those are our symbols. What's nice about the symbols is their charges are indicated. But the charges have value, and we'll get to that in just a second. All of the masses in the nucleus. Nelda and Patty are about the same size. We say that they have a mass of 1. Nelda's a little bit, tiny bit bigger, but they're almost the exact same size. Electron Elliott, the electron is so small comparatively that we say it has a mass of 0. It's negligible. The value of the charge on a proton is +1, a neutron is 0, and an electron is -1. And the location of protons and neutrons are in the nucleus. And we will say that the electrons can be found within the electron shells. Eventually, you're going to get a whole different picture of what the atom looks like, and it's quite a bit different than this, but this is valuable for us right now. I've probably already turned your life upside down a little bit by telling you that there are 18 electrons in the 3rd energy level. I heard, was that you that said it? I thought it came from that direction, but I wasn't sure who said it. Okay, so what else do I need to teach you? I need to teach you some definitions. If we look at a periodic table, I'm going to use aluminum for an example. If we look at a periodic table and blow up the box for aluminum, I'm going to look at this one right up here. I see a 13. I see an AL. I see the word aluminum. And I see a 26.98. Does anybody know what this 13 stands for or what it represents? Noah?
Atomic number.
That is the atomic number. What is significant about the atomic number, Megan? It is the number of protons. If the atom is neutral, like if we have the same number of protons as electrons, then the atomic number also indicates the number of electrons. So a definition, the atomic number is the small whole number on the periodic table. It indicates the number of protons in that element. Are you guys okay with the shortening of things? I think the less that we can write, the better. Makes our lives a little easier. You know that number means number of protons, E's with a plus. Also, if the atom is neutral, indicates the number of electrons. One thing that we're going to learn to discover is that if there aren't 8, it's not great. So if an atom doesn't have 8 electrons in its valence shell or its outer shell, it is generally not stable. All right. So let's have this Matterville represented by aluminum. How many positive patties are there? 13. We have 13 positive patty protons. How many nerdy Nelda neutrons? What did you say?
Huh?
What did you say?
Can't see it.
How many nerdy Nelda neutrons? Okay, you're saying 14, and why are you saying 14? Okay, so you're looking at this number right here, right? This number right here is the atomic mass. And I can have different types of aluminum. I can have aluminum with 15 neutrons. I can have aluminum with 14 neutrons. I can have aluminum with 13 neutrons. So it doesn't matter, as long as there are 13 protons, the number of neutrons can vary. So in any sample of aluminum, some of them are going to have 13, some will have 12, some will have 14, some will have 15. Neutrons can vary, which means that their mass can vary. So this number right here is called the atomic mass. And the atomic mass is the average mass of all types of an element. In general, the one that's most common is probably going to be the one that we would round the nearest whole number to. So we're going to say 27. So that number with the decimal is called the atomic mass. It is an average mass of all of the different types of the element. But there's another number called the mass number. The mass number is coming from our nucleus arcade, where all of the weight is, all of the mass is equal to the sum of the numbers of protons plus the numbers of neutrons. At this point, to get a mass number, as you've done in the past, we'll look at the atomic mass and we'll round it to the nearest whole number. And that will allow us to choose the number of neutrons for a particular element. All right, so the next thing that I want to teach you is something called a complete chemical symbol. Now, I realize that this is not the most riveting of topics, but I promise you that I don't spend time teaching you things that I don't think are valuable. And I'm adding to a foundation that's going to set you up for success within this week even. So this is called a complete chemical symbol, or a complete symbol. The complete symbol has the element symbol. It has the mass number right there, and it has the atomic number right there. So this is the complete element symbol. So I'm going to hand something out, and it's going to seem like busy work. But I don't believe in busy work. I wouldn't ask you to do it if I didn't think it was not valuable, or if I didn't think it wasn't valuable. If I thought it wasn't valuable, I would not ask you to do it. I have a hard time today. Okay. Notice here, it says making a periodic table. This is for the first 18 elements. And they go in order 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Now, we're going to work on this for the rest of this hour, but you have to promise me that you will not do it as homework. Got it? All right. Don't work ahead, as tempting as it may be. Work on it in class today and then bring it tomorrow. I don't want you to continue to work on it at home. So what we're going to do is we're going to draw a basic atomic structure for the first 18 elements with the complete chemical symbol, the name, what's in the nucleus, and how the electrons are distributed. Now you'll notice here it says the number of electrons distributed in shells using a 288 format. That whole idea of 288 isn't so far out there that it wasn't, the little white lie that's been told to you is not really harmful in any way. In this particular example, you're not going to have any more than 8 valence electrons. What is a valence electron? Yep, the electrons in the outermost energy level is a valence electron. So let's do one together, and then I will set you guys loose to work on one. So let's pick one between 2 and 16. 16? 16 it is. 16 is 1, 2, 10, 11, 12, 13, 14, 15, 16 is going to go right here. And
do 16, it's right there.
Huh?
It's not do 16, it's sitting right on the page.
no, it's not, because that's number 8.
I wanna do 16.
All right, 16 is sulfur.
Squeeze it. Squeeze it.
And if I look at the symbol for sulfur, I see that the atomic number is 16. It says 32.07. I'm going to round that to 32. So I have my complete chemical symbol. Now the next thing that I'm going to add is what's in my nucleus. I have to draw this circle big enough to be able to see it. If you can draw as small as I did in this example, that might be a good size. So I have protons and neutrons in the nucleus. The question is, how many of each? How many protons? 16. If my mass is 32, and I have 16 protons, how many neutrons do I have? 16. What if my mass was 33? There would be 17 neutrons. Okay? This is a neutral atom. How many electrons?
16.
16. How many can I fit in the first energy level? 2. When we add these atoms, I want everyone to add them the same way. 1, 2. In the second energy level, top, bottom, left, right, top, bottom, left, right. That gives me 10. That electron shell is filled. The third energy level, I still have 6 electrons that I need to add. 1, 2, top, bottom, 3, 4, left, right, 5, 6, top, bottom. If we all put our electrons on like that, we will all have diagrams that look the same. And again, you may want to bring a pencil or something tomorrow, or some whiteout in case you make mistakes. Because we are going to do this for the first 18 elements. Closed-toed shoes tomorrow, we will be in the lab. Bring some money for goggles, or goggles if you have them. Also, your lab safety contract signed if you haven't done that yet. And don't do this. This one where you learning how to name compounds first. All the elements and compounds left.
Okay.
So we're just gonna look at compounds.
I want to do this actually.
No, you're gonna do that. Like you're gonna go from station to station and mix it.
Okay, that's